In this lesson, we're going to expand on our skill sets for doing regressions for sets of data to see if we can determine which model best fits a data. So in the last couple of videos, we learned about regression from a simplistic standpoint, looking only at linear. So I want to begin today's lesson based on what we already know about linear regression. So we know that the general equation for a linear system is y equals mx plus b. And we learned in Desmos that if we want it to perform a linear regression on a set of data, that we have to make three key changes to it. We have to indicate which y column we want the data to be regressed with. And if your table is the first table you've entered in Desmos, the column will say y1. We also have to tell it to look at the x1 values that correspond to those y1 values in the data table. So those are two of the changes we make. In order to make it a regression as opposed to an equality, we introduced to you this little tilde sign, which can be found on the Desmos keyboard, but also on your regular keyboard as well, to the left of the number 1 key, using the shift. Linear regressions or linear data sets have two simple scenarios. They can have a positive regression, and they can have what I would consider to be a negative slope or a negative regression. In this one, as the independent variable is increasing, so is the dependent variable respectively. When there's a negative slope, as the independent variable increases, the dependent variable is decreasing. So today, let's add on to your toolkit of regression tools to see if we can use other models to explain data as well. The next one I'd like to look at is quadratic. And quadratic, I'm going to put a little star beside it along with linear, are regression equations that I want you to know. They would not be given to you on a summative assessment. They are equations you've seen before, and if you just make those three minor changes to them from their general equations, you can come up with the regression equations quite easily. So for quadratic, in previous math courses you may have learned you can express that relation in vertex form, in intercept or factored form, and also in standard form. We're going to use standard form as our general equation. So as a recall, it looks something like this. Y equals ax squared plus bx plus c. So again, if we want to come up with a regression equation to use in Desmos, we make our three minor changes. We tell it to use y1 values from the table of data we entered to Desmos, and for all of the x's, we also have to put y1 as well. Okay, so it appears in two locations here with quadratic instead of just once in linear. And then the third change is to use the tilde relationship or the regression relationship instead of an equality. So your regression equation in Desmos looks like this. With quadratics, there are two scenarios, of course. You can have a parabola that is right side up. You could also have a parabola that is upside down. Okay, and they can be, of course, located anywhere in the Cartesian system in terms of the four quadrants. I've just drawn these as examples. Okay, so you would see a parabola. It's either upward with a positive a value or downward if it has a negative a value. Another regression equation that I'd like us to explore is one called a power relation. And the general equation for a power relation is y equals, before power, let's do exponential first. I'm jumping ahead of myself here. Let's do exponential. Again, this is one that I want you to know. The general equation for exponential is y equals a to the x, but a better version of it is y equals a times b to the x. Okay? The b disappears here only if b is equal to 1, and that's not always the case. If we want to change this into a regression equation, we do our three changes. We do our y1, regressed against ab, and then we have to have x to the 1 up here as well. There are a couple kinds of exponential relations that you may have encountered in previous courses. I want to focus on ones, of course, that are in the top right quadrant. You could have something here where you have an initial population of, say, a bacteria, and over time it grows exponentially. This is a curve that in our day and age right now with the coronavirus, you're seeing a lot of on graphs that are being shown in the media in terms of the number of cases or the population versus time. Another exponential one that can happen is you can have a starting population or a starting quantity and have it decrease over time. Okay, so this one here can be related to population growth, or bacterial growth, or viral growth, and this one is one that we see in chemistry for half-life, or the decomposition of radioactive materials over time. Okay, the next one that we're going to look at is a power relationship. So you'll notice again I have a star beside these four. These first three are the key ones that we're going to use. Sometimes power and exponential can have similar results, but I want to expose you to it as well. Power relationship is y equals ax to the b. So you notice it looks very similar to this one, except that the b and the x have changed places in this particular power. So again, if you want to come up with a regression equation, it would be y1 regressed against a, x1 to the b. And a rough sketch of a power relation could be something like this, where it starts over here and goes up in some type of curved nature. There are a couple more that I'm going to expose you to, but that are not going to be the focus of our course. The next one is, I'm going to skip in your note here and do cubic first. And then we will end with polynomial. And then we'll have a little chat about polynomial at the end. Okay, a cubic function has the general equation of y equals ax to the cube, or to the third, plus bx squared, plus cx plus d. Okay, and again, if you want to make the regression equation, you do the three minor changes. Make this a y1, make all of your x's x1, and add your tilde, and you've got it. And again, if you had more than one data set, these ones might become 2s or 3s, depending on which table you're referring to in decimals that you've entered. The general sketches of cubics are pretty fun. And again, this is not the focus of our course, but nonetheless, I'll expose you to some types of cool relationships you might see. Okay, so often when it comes to cubic relations and data sets, we're often looking at a piece of it and not the entire thing. Again, I think we'll just leave the conversation to stop there. Now, polynomial is kind of the end-all and be-all. It allows you to begin with any power beyond cubic, so x to the fourth, x to the fifth, and so on. So it's like cubic, but you're going to decrease the power of x by 1 in each case. So a cubic is an example of a polynomial. So is quadratic, but this allows us to go to higher powers. And we go on until we get to plus z, right, as much as you want to. Again, I don't want this to be the focus of our course, and I'm not even going to put it into a regression equation, okay? And I mean, the way that it looks will depend on the initial power that you start with as well. So skipping down to polynomial on page 2 of your note for a moment, there are some limitations of polynomial regressions that you've got to be very careful with. They often fit data sets really, really well, but they don't always make the best model because beyond a certain range of x values, it just doesn't make sense. So we have to be very, very careful if we use them for extrapolation beyond data points within our set. And so the other thing we have to watch too is that because we've got all kinds of curves, it's often useful to explore regressions for all of them and critically analyze them all together at the same time to see which one's best. Often polynomial will look the prettiest, but you have to also read into its context as well. So just be careful with polynomial regressions. Instead, as I said for the course, I'd like you to focus in on, sorry, I don't want that one to be starred, power, exponential, quadratic, and linear are your 4 main types of regression. Before we leave this lesson, there's one more thing I want to note for you, and that is when you put these regressions into Desmos now, you are going to get an output called the coefficient of determination. Okay, so when we looked at linear relations before, we were able to decide how close that data fits by looking at the R value. And we know that R can have a range anywhere from -1 all the way up to +1. The closer it is to these extremes, the better. Okay, these become perfect correlations if they're equal to 1 or not. So again, this is called the correlation coefficient. But as soon as we get into other types of regressions that are nonlinear or have a curved nature to them, we are going to use the measure of the coefficient of determination as being a measure of how close data is. And this is different because R squared can have ranges from 0 to +1 only. It can't have any ranges of -1. I mean, think about it. If an R value is negative and you square it, it becomes positive. So the closer a data set is to having an R squared value, of 1, the better that model fits the data. And again, just using some terminology here, this is called the coefficient of determination. Okay, so be mindful. You want to look at R squared for nonlinear regressions. You want to look at the R value for linear regressions. In the next video, I'll show you a Desmos screen and I'll walk you through how to work on page 3 of your handout using linear, quadratic, cubic, and exponential regressions.